Welcome back to the second part, and now we're starting to speak about functions. A function is defined by the keyword def. Def, name, open paren, parameters, close paren, colon, body. Note that the parentheses are mandatory. Even if you have no parameters, you just write def, name, open, close. That's all there is to it. The body gets compiled at the time you execute def. It gets compiled and connected to the function object that is created. The function object is also assigned to the name that you're giving. It's not executed at this time. Later, as in late, not necessarily after that in your program text, but later in time, you can call the function. The call is, the syntax is simply name, open paren, arguments, close paren. Again, the parentheses are what makes a call. This is going to be familiar to any C or C++ programmer. If you just mention the name, you're mentioning the object. You could put the function object in a list or something. If you want to call it, you have to have parentheses there. The arguments and parameters must correspond. Arguments are what you are values that you are initializing the names in the parameters with. Their correspondence is typically one-to-one, but there's a few ways that you can use more flexibility there. The parameters at the end can have default values, like in C++. So you can use the syntax parameter name equal expression, meaning unless otherwise specified, this object is the value for this parameter. Be careful, this expression is evaluated once at the time you run the def statement, and that object is going to be used for every call that doesn't specify that name. You may or may not override this by explicitly specifying a corresponding argument in the call. Similarly, the last few arguments you give can be named. Instead of just taking the positional corresponding first argument goes to first parameter, second argument goes to second parameter, you can say explicitly what parameter name you're setting to the value you're passing. Finally, you may define a function that takes arbitrary positional and or arbitrary named arguments. The syntax is star name. It will give you a tuple name of extra positional arguments, and star star name, it will give you a dictionary of optional named args. So there's a lot of flexibility there, which is typically used, for example, to wrap a function in another function and pass arguments through without needing to know which ones they are. Here's a simple example. Totally elementary function takes two arguments, does the sum of squares. So that's all there is to it. But it's not very general. It will work if we're in the middle of computing a hypotenuse. But what if we have more than two numbers and we want the sum of their squares? This is the Pythonic way of expressing that. The sum of squares, arbitrary arguments, is the sum of the square for every item in the arguments. So the sum of all squares is the sum of the square of each item. That's just about as high level as you can get and stay general. If you're used to lower level languages, you may think in these terms. Well, start with a total of 0, then go over all arguments, incrementing the total by the square, and finally return the total. That will work too. As I said, we do bend over backwards to try and support people who are so attuned to lower level programming languages that they can't just express their problem anymore. But the problem you're trying to solve is this one, and this is much faster and much more natural in Python. So if you find yourself basically writing Fortran in Python, try and write Python instead. It's going to be much faster and make you much happier. Generators are functions which, instead of returning a value, yield values. The keyword is yield, Y-I-E-L-D, instead of return. What's the difference? A return gives a result and terminates the execution of the function. A yield gives a result and suspends the execution of the function at that very spot until further notice. Specifically, the mechanism we've used to let you resume and get the next result, the next thing to be yielded, is iterators, which are basically objects with a next method. So when you call the generator, you get the iterator. Every time you call next on the iterator, you get the next thing to be yielded. And when everything is done, when there is no more next value, the iterator will raise a stop iteration exception. If you use a for loop, remember the definition of the for loop that we gave in the first half, this is basically done for you for free. So I mentioned enumerate before, it's actually a built-in, but if it wasn't a built-in, these are two ways we could actually program it. One is the lower level way, the other one is the higher abstraction and faster way. So job of enumerate is yielding each item of the sequence with its index. So 0, first item, that's the first yield. 1, second item, second yield, and so on. So you could think, well, I'll start at 0, loop over the sequence, and yield the current index, n, and the item, and then increment for the next time. So when the yield executes, the function freezes. The execution of that particular run of the function freezes. And when the next method is called on the iterator, it continues by incrementing and going back. This is the higher abstraction way of doing it. It uses the standard library module iter tools, these tools for iteration, to do a element by element parallel zipping, and count, which is an iterator which yields the unending sequence 0, 1, 2, 3, and so on forever. What we're doing is zipping the sequence 0, 1, 2, 3 with the sequence we were giving as an argument. So this single statement does the job of these four. Again, think in these terms. When you program in Python, you'll be so much happier. Let's give a slightly less elementary example. One of my favorite mathematicians of all times, Leonardo Pisano, known as Fibonacci, wrote an exercise in his Liber Abaci about computing the number of rabbits produced by a hypothetical rabbit warren. You may be familiar with the Fibonacci sequence. It's basically the sequence here. So it starts with 1, 1, and then every item is the sum of the previous two. So this is a low level but perfectly acceptable way of programming. We'll start with I and j both equal to 1. Note something I hadn't mentioned before. You can chain assignment, like in C. I equal j equal 1 gives the both names I and j to the object 1. And then while true, which is, of course, means this loop will never terminate, not per se, we do another form of multiple assignment. We assign I, j, and I plus j to r, I, and j, respectively. If this isn't perfectly obvious, the right-hand side with the multiple values is evaluated left to right, so I, and then j, and then the sum. And after all the evaluations, then all the name binding. So r is I is j is I plus j. You could write it as 3 assignments, but there's no point. And finally, we yield this current result. If you just did a for on this will run forever. So it is crucial that the for has a break inside it at some point when you have enough stuff. So this is, as I mentioned, the purpose of the exercise was computing the number of rabbits born in a farm in a certain year. So for rabbits in Fibonacci, note we have to call it to get the iterator. We just print it with a comma to avoid breaking the line. And then we decide when to break. We break when we have more than 100 rabbits, because that's a large enough farm And this is the result sequence. Another trick, which will be very familiar to JavaScript programmers, but is not common in the other languages. Def is an executable statement. I did mention there's no such thing as a declaration. Everything is a statement. Def is an executable statement. Every time def execute, it builds a new function object and binds it to that name. Also, scoping is lexical. That is, if I'm looking for a variable name and it's not bound in my current context, I go to the context containing it, where contexts are functions in Python. So, consider this. Def make adder given an addend. When def make adder compiles, it just compiles this. When def, the outer def executed, just compiles this. When make adder gets called, this def executes, meaning this code gets compiled and bound to name adder, and that name adder of an inner function is returned from the outer function. This is known as a closure. The inner function adder doesn't have anything named addend, and so it looks outside and finds it in the outer function. So for example, a23 equal make adder of 23. Now a23 is a function that will sum 23 to whatever it's given. And similarly, make adder of 42, so now a42 is a function that will sum 42 to whatever is given. So we can print a23 of 100, a42 of 100, or compose them. They're totally independent now, because every def, every time the inner def runs, it builds a new function object. The two don't interfere, so we have the expected results. A syntax form known as decorators makes higher order functions even smoother to use in Python. Basically, whenever you write @decorator def something, or in Python 2.6, which is about to go beta now, similarly for @decorator class something, but we won't be covering anything beyond 2.5. Whenever you write this, it's as if you've done your def, so created your function object, and then rebound the same name, which you used in the def, to whatever happens passing the function object as the argument to the decorator. So basically, decorator has to be a higher order function, or it could be a call to a function returning a higher order function, higher order squared function. This is very handy syntax for all sorts of things. Particularly it's used inside classes, as we'll see. A class, okay, there's new style classes and old style classes. I will not be mentioning old style classes at all. They're totally obsolete, only exist for backwards compatibility. We'll talk about new style ones. A class is similar to a def in a sense. It's also a keyword, class, the name, and then basis in parentheses. If you have no basis, well, you should always have at least object as a base. So at the very least, you'll have open paren, object, close paren, and then a body. So it's different from a def in this sense. As I mentioned, when you execute def, the body only gets compiled, not executed yet. When you execute class, the body gets executed. The body is typically a series of assignment and def and possibly other statements, and it's executed at the time you execute class. It basically binds names to values, and those names become attributes of the class. So functions, for example, become methods for the class. Also, anything that is an attribute of a base is also found when you look up at things on the class itself, except that you can override, just like in C++ or Java. If something is defined in a base class and you define it differently in the derived class, the derived class wins. So in C++ it's slightly different because you explicitly have to say that something is virtual. In Python, like in Java, there's no such need. Everything can be overridden. Let's give a very boring example just to show. So class EG, because it's an example, inherits from object, means it has no real basis, just the most generic object of them all. It starts with assigning an empty list to CLA. So that's a class attribute. The class itself owns a list. And then it has a def with a special name dunder init dunder. That's the initializer for the instance of the class which is called self. And so it binds a new dictionary, empty dictionary, to self.ins, which is an attribute of the instance, not of the whole class. And then we have two methods. One does append to the class attribute, and this one does an insertion into the instance attribute. How we instantiate classes is simply by calling them. There is no need for such redundant operators as new. We just call the class, and each time we call the class, we get a fresh new instance. So having just instantiated them, I see that the CLA of the instances is the empty list, because since the instance doesn't have one, it goes back to the class, and the ins are empty dictionary, was one per instance. Once I've called a few methods, note that the CLA is the same for both, while the ins has changed because one is a class attribute and the other is the instance attribute. So if I ask, are they identical objects? Are they the same object? For the CLA, the answer is true, because they both go to the class. While if I ask it for the ins, which is by instance, then the answer is false. They're not the same object. When Python is kind of peculiar among very high-level languages because it tries to make everything very explicit for you. Remember that rule in the Zen of Python, explicit is better than implicit. In particular, what does it mean to look up an attribute on something is very clearly, very detailedly specified. So for example, normally something like inst.method arg1 arg2 will be exactly like looking up the method on the type of the instance and passing the instance as an implied first paragraph. More generally, whenever you do inst.name, whether you are about to call it or not doesn't matter. There's a single namespace for executable and non-executable attributes. First of all, the string name is looked up as a possible key into a dictionary which belongs to the instance. Every object, just about every object, owns a dictionary with a special name dunder, which is basically where all of its attributes are organized. If it's not there, then we try the same thing for the type, that is the class. Type and class are more or less synonyms in Python, except class is a keyword and type is a normal identifier. If it's not there, then we try exactly the same thing along all the bases. The base classes are recorded as one of the attributes of the type as part of the class statement. If we haven't found it in any of the bases, then we try a special method, dunder dunder, which is basically there to let you compute attributes on the fly, just in time when necessary. If that works, then it's a result. Otherwise, you finally get an attribute error, which is an exception, meaning that attribute name does not exist anywhere in the search space for this instance. Now, subclassing, and this is where overriding gets in, means you can specify that EG is a base class of sub, and then you can define the same thing, same name, meth2 in this case, that you had already defined on the base class, and this is an override. In the override, you can call the method on the base class explicitly by base class dot meth2, and remember in this case you have to pass self explicitly, or you can do it implicitly with a super, which is a kind of a magical piece of magical built-in, which does the lookup in the base classes for you. So another example is that you can override data as well. So I've defined a subclass of list where every append is actually done twice. So basically, every time you append something, it's appended twice to the list. Not particularly useful, just an example. The point is to show that when you subclass, you can override a piece of data, in this case CLA, just as much as you can override a method. Again, there is no distinction. Just define it with a different name. Every use of that attribute will use the overridden attribute. Another very useful concept is that of a property. Suppose you have two methods, we call them getter and setter. Getter just takes the object and returns a value. Setter takes the object and a value and somehow sets the value appropriately into the object. You can give a very nice syntax by calling the built-in property with a getter and setter as part of the class, assigning it to a name. Now, every time you access that name, instant name, Python internally calls the getter method for you. And every time you assign something to that name, it calls the setter method for you. So that's very nice syntax to be substituted to function calls, to method calls. Note that I did say you cannot override the equal. That only applies when the left-hand side is a simple identifier. When the left-hand side is like here, a attribute access, you can actually do pretty advanced stuff even to the assignment, and property does it for you. Why am I dwelling so much on properties? Because there's a meme going around, particularly in Java, but to some extent in C++ as well, that you should not expose attributes. To keep flexibility, you should hide attributes behind getter and setter methods. Thanks to properties, this is useless in Python. You just expose the interesting attributes directly. If and when you need a getter and a setter, you write them and you wrap them into a property, so that all client code using your class doesn't need to be changed. It can still assign to attributes, C attributes, and the method calls will happen intrinsically on your behalf. Avoid boilerplate. Don't waste pixels. Do not code this kind of thing. Just name the attribute without a leading underscore so it's visible, and let people use them, and wrap it if and when that becomes necessary. I did mention Python has operator overloading. How does it do operator overloading? Is by defining a huge number of special names. Special names start and end with two underscores. Two underscores, you could say underscore underscore, but that's a bit long, so a common way of pronouncing it is dunder, for double underscore. Anything beginning and ending with dunder is reserved to the Python language, so do not use this form of identifier for your own arbitrary names. They could conflict with special names in the future. There's a lot of things you can do in special method. There's a constructor, new, initializer, init. Note there is a difference between constructing and initializing. If you're familiar with the so-called two-step constructor design pattern, Python gives it to you. New actually makes a new object that's still bare, and init lets you initialize the object. Del, which is what happens when the object goes away. It's not a destructor, it's more of a finalizer. If you're familiar with C++ destructors, that's a bit different. This is more of like a Java finalize. And then various ways to convert things, not just to wrapper, string, int, float, complex, and so on. Many ways to compare things, less than, greater than, equal. A lot of method for arithmetic, addition, subtraction, multiplication. Methods to make it like a function, so callable, hashable, so it can go into a set or dictionary. Dealing with attempts to get set and delete attributes or items, as in a container. Other container stuff. Get and set to define what are called descriptors. Enter and exit describe what are called context. So there's a huge number of special methods you may want to define. The point to retain, you will find out the special methods, which are basically high syntactic convenience if and when you need them, that Python will call the type special method for you when you attempt the appropriate operation. So, for example, when you write foo open close, Python looks up the type of foo, finds the dunder call method, and that's what gets called. It would be like operator open close paren in C++. And sometimes it does so in a more structured way. For example, if you ask if A greater than B, and A doesn't have a GT method, Python continues by looking if B as an LT method, so that it's basically going to compute as a second possibility if B is less than A rather than if A is greater than B. More generally, built-ins do things right for you. But let's get a simple example first. Remember the Fibonacci generator we did a few minutes ago? This is the same thing done much more detailedly as a class. At initialization, we set 1 to I and j. It's got to be self I and self j because they're instance attribute. We have to specify it's an iterator by saying if somebody wants to iterate on me, use me directly. And then there's the next, which is unfortunately not marked by dunder. This is fixed in Python 3.0, but this is in Python 2. We didn't place the double underscore, but it is a special method because it's called, for example, by the for loop. And this does essentially the same thing that we did more simply in the generator, but it does it explicitly with self-dot variables. And this is basically intended to be used in exactly the same way as the generator I gave before. So it's exactly the same semantics. Basically what the generator does is generate for you an object which is more or less like this. Okay, built-in functions are what calls the special methods. You never call a special method directly, essentially. Think of the double underscores as a way to make special method ugly. So you're not even tempted to call them. Never call x dot dunder len open close. Call len open x close. It will do the right job, which in this case is calling dunder len. Another example, abs. Don't call this directly. You don't really know what the abs built-in does. It will probably call dunder abs, but suppose it doesn't find it, it may be able to do a change sign, test if greater than 0, change the sign for you. It may or may not, but always go through the built-in function. There are a lot of built-in functions, not just ones corresponding directly to special methods. We'll see some of them in examples. And also, these are just the ones that are always available to you, but there's a lot in the standard library that you want to use just as much. These are all absolutely crucial modules in the standard library you'll need to be very familiar with to do effective use of Python. As I said, rather than going into these in details, I like to give an example. Suppose we have a readable file somewhere. We'd like to make an index, that is a map from the words in the file to the line numbers where that word is found. So first we build the map and then we emit it. To build the map, we start with an empty dictionary. Dictionary is a natural way to represent a mapping. We use a with open file name as f syntax to open it and guarantee it's closed as soon as we're out of this with block. We use enumerate to get line numbers. And in generally, looping on a file gives you the lines of the file, so strings. And then we call the split method, which breaks a line into a list of words and to loop over that. And here we use the set default, which is a bit complicated, because basically what it does is it looks up this key in the dictionary. If it's there, it returns what corresponds to it, the corresponding value. If it's not, then it sets the second argument as the new value for the key. So it's kind of complicated. But basically, you take either a list already corresponding to the word or a new empty list. In either case, you append the line number to it, so the line numbers accumulate. And then, once we have our index, we can just emit it to standard output in alphabetical order. So for that, we use a sorted built-in, which given any iterable lets you loop on it in a sorted way. So sorted order for strings is alphabetical. So you loop on the words in order, and you print them. I'm using the % formatting here just to have a colon attached to it. And then we print the line numbers. Note the comma here so we don't break the line. And finally a print without anything just to break the line at the very end. We can do it slightly simpler if we're familiar with the standard library, because the collections module has a subtype of dict known as a default dict. A default dict is something that if you try to index it and the index isn't there, the key isn't there, instead of raising a key error, calls something to make the new item. In this case, we want to call the type list without arguments to make an empty list and set it there. So once we've made a collections default dict of list instead of a plain dictionary, we can simply use index word append n instead of having to go the complicated set default route. Everything else, every other bit of code in this slide is just the same. Other things we could do that could be interesting, so once we have this index, what about giving the 7 most popular words in the text files? What are the 7 words that appear on most lines in this file? Well, for this purpose, we want to use heap queue. Typically, it's a typical priority heap operation if you're familiar with your algorithms. And specifically, it's exposed as heap queue n largest. Give me the n largest items of a certain collection. And the n we want is 7, the collection is index, and we get to define what is the key extractor for the comparison. So key equal index get means we're not getting the 7 alphabetically largest, but the 7 whose corresponding value in index is largest. And this will work. And this is an nwalk form that is, I don't want all the lines with the word rabbit or all the lines with the word hare. I want the lines with both rabbit and hare. How am I going to find them? This is a set intersection problem. So I'm basically going to simply make a list of all the words I'm looking for, pop the first item, and make a set out of the corresponding line numbers. And then I'm using the ampersand operator to do intersection, specifically in the form ampersand equal, so intersect in place. Basically, all binary operators have an equal form. So, for example, plus equal increments in place, and ampersand equal intersects in place. And in the end, of course, I'm careful to sort it so it will print out nicely in alphabet in line order, because the set, by making a set, I get very fast intersection and so on, but I lose the significant order, because a set is a hash table, so it basically, as I mentioned, doesn't have an intrinsic order. But when I do need it, I can always sort it on the fly. So I mentioned that the standard library is full of very useful modules. To access anything in the standard library or any other module, you have to import the module. And this is how you do it. I already showed it in a couple of examples, but import module name is the canonical way. So, for example, when I wanted to use something in collections, I started with import collections. This basically makes the name collections available to my program. And the name collections refer to that module, so then I can use the attributes of the module in my program. If a module is contained in a package, we'll see exactly what a package is in a second, then I cannot just import it because it's hiding inside a package. I have to tell Python from what package to import it. The package, would be a package named package, inside a package named given, inside a package named sum. So sum.given.package, Python would look for sum, inside it for given, inside it for package, and inside that for module name. In either way, you basically get the module name as part of your namespace, and you can access it. And then you want function blah from the module, just do module name.blah, and you're done. So there are some other ways. I did mention that we'd rather have only one way, but sometimes it's kind of inevitable to offer more than one. Although in practice, these two will make you happy all the time. You should be aware of the others because you'll see them used in Python examples and code. One possibility is you can import the module under an assumed name. basically put a false mustache on the module so it makes believe in your namespace that it's named something different. And that is the as clause. So for example, suppose somebody gives you a name that is, this name is far too long, and this name is far too long to use conveniently, and you would like to have a shorter name for it. This is how you do it. Import this name is far too long as Z. And now, instead of this name is far too long dot blah, you can use Z dot blah. And this is indeed sometimes useful if you ever have to handle modules whose names are far too long. Two alternatives I don't recommend is, instead of getting the module into your namespace, reach into the module namespace and grab one thing into yours. From this name is far too long, import blah. This will work, but throughout the rest of your code, people who are reading it, including yourself when you're maintaining it in 6 months, will wonder, where's this blah from? And you will have to go and look for when it was imported. So I'd rather always see module name blah or z.blah to get the immediate thing. It's not a top-level name. It's coming from something else. And the very worst thing is to import star, which basically grabs all of the items in the namespace and injects them into yours. Don't do that. That is a guaranteed way to cause yourself headaches. It's handy if you're at the interpreter prompt, because say you're doing a lot of math at the interpreter prompt, you don't want to say math.sin, math.cos, math.tan, math.atan. You want sin, cos, tan, atan, and all the mathematical functions to be part of the top namespace. That's because it's too much typing otherwise. That's possibly the only reasonable ways to use the import star. And this is, to clarify what just, so I want to compute an arctan with 2 inputs. The normal way is to import math and then use math.atan2 of x and y, which in this case is this value. If I tried, even after importing, to just use atan2, this would give a name error exception, because in my current namespace, there is no name atan2 defined. Remember, I got math into my namespace, but atan2 is still within namespace math. I could do from math import atan2. In this case, this would inject atan2 in my namespace. Sometimes when you're doing this interactively, like at the prompt, it's kind of nice. In real programs, it tends to be confusing, and this goes squared. From math import star, now you have 25 mathematical functions in your namespace, which is handy, but don't do it in real programs, only in interactive use. So this is all nice about how I use other modules, but how do I make my own modules? Well, that's easy. Any Python program is a module. Any what.py is a module. Just put it in the appropriate directory, say the same directory as the one is being imported from, or the rules depend a bit on, but for Google App Engine, that's what you do. And then any other module in that directory can do import what, and Python will look for what.py. The directories are listed in syspath, and they need not be directories strictly. In general, they could be zip files. So instead of having a file system, you can basically zip everything up, and Python will find it anyway. That's kind of handy. There are other things that you can import. You could import bytecode files. You could import files coded in C or other languages for Python. So the extensions are pyc, pyd, or sometimes .so on Linux. But this wouldn't work in Google App Engine. Google App Engine only accepts the .py files. So you want to make sure you place the .py itself. It handles the compilation to bytecode and making sure the bytecode is secure and everything else under the covers. So this variant is nice for other kind of uses of Python, but don't rely on it on the application engine. So what's a module? Well, it's an object. Everything is an object. It's got attributes. That's basically everything it has. It doesn't have anything sophisticated, only attributes. The attributes of the module object are what you could see as the top-level names of the module as a source. So for example, say we have a module whose .py source is only x equals 23. And this is called what.py. If we import what, then the only thing there is in it is what.x, which is 23. And that's all. Besides assignment, names can be bound by class, def, import, and from. Class name binds the name, def name binds the name, import name binds the name, from foobar import name binds the name. The attributes of a module are also known as the global variables of that module. Note, there is no such thing as global globals in Python. Globals are always per module. Within that module, you can, of course, access them as bare names. From other modules, you will access them by module name dot variable name. Note again, well, variables, but can they be functions or classes? Yes, there's no distinction. Names are names are names. Whether they're callable or not, they're just attributes. You can also bind and unbind module attributes from the outside, a practice known as monkey patching. I would strongly recommend against that in production code, unless you're fixing some bug in a library which you're not allowed to edit. Don't do it. Sometimes it's handy for testing, but there are better ways. Use the dependency injection design pattern. You will do your testing in a much more systematic way. I would strongly recommend avoiding monkey patching. If you look for monkey patching on the web, you'll find very strong diatribes for and against it for every language that's supported, which besides Python include Ruby, JavaScript, and so on. It moves a lot of emotion. Basically, people who are programmers at heart don't want to do it, but all these languages are used by people who need to program but aren't programmers. They're like hardware experts or web experts and so on, and they don't see why they should do things the proper way. But I'll leave that to the web. It's important to notice that modules are singletons. They are the most natural and Pythonic form of singletons. They're automatic singletons. What does it mean? It means that if you import a module more than once, the first import is treated very differently from all the following ones. The first import finds the module somewhere, loads it, compiles it on the fly if needed, or takes the compiled form, executes the body of the module so the module object is properly populated, and places the module in a system directory known as sys.modules. Sys is itself a module, so you can import sys if you want to play around with it. And sys.modules is a dictionary. The keys are the names of modules. The values are the module objects. So when you import the module again, Python will first look into sys modules. It's very, very fast to check if something is in a dictionary. If it finds the name, that's what it gives you immediately. It's basically one instruction. No second loading, no further execution, instant. Your singleton is right there. So some people love the singleton design pattern and says, well, yeah, this kind of works, but it only gives me a module. I can't use a class instance there. So for example, I want my singleton object to support addition or greater than comparison, and I can't do that because modules are simple objects. Even if you define a function called under, add, under, it won't do anything. It's not a special, because it's not part of the type of the module. And remember, the special methods only work if they're in the type, not in the instance. So, this is how you stick something that's not a module into sysmodules. Some people consider it a trick. I consider it a perfectly legitimate use of a mechanism that Python exposes for your users. Of course, it's a very advanced one, but it's a way to make... Oh, by the way, dunder name is a special attribute, which is the name of the current module. And that's how you basically make your class, an underscore in front just to indicate it's actually private and intended for internal purposes. And there you go. Packages are essentially modules containing other modules, and of course there is no limit to nesting. You can do this way. So you can have sub-packages and so on. In practice, it lives typically in a file system, or it could be in a zip file, in a directory. And how you distinguish directories which are just directories from directories which are packages is by the presence of a file called dunder init, under.py. Python will only consider for package search a directory which has a file by that name. So that file contains the module body. It's often empty because you don't necessarily want the package to do anything else than containing other modules. And so you don't need to do anything in initpy, but you still need to have it there because it acts as a flag to Python that, yes, this is not just any directory, this is a package. The modules inside the packages are basically all the py files in that directory. And that is done for you by Python, so you don't need to worry about it. And if you want sub-packages, you will have subdirectories, which in turn need to contain the special dunder init dunder file. Note that the parent directory of the directory package must be on the syspath. And once you have a package foo with a module bar inside it, you could import foo.bar. That will work. We'll bind foo.bar in your, so you will bind foo and give it an attribute bar, but a more common approach is to use a from foo import bar that only binds the name bar directly. So basically, I like my imports to always bind a module to a name, and this is what it does. Okay, now we've basically covered, well, so to speak, the Python language, and a little bit of the built-ins, and a very tiny fraction of the standard libraries. One of the mottos of Python is batteries included. It means that the standard Python library has more than 200 modules. That's production modules. There's many more for unit tests, encoders, decoders, demos of various kind, and so on. Some are pure Python, some are coded in C. The application engine will support any pure Python module, and most C-coded modules that are part of the standard library. There are specific limitations that will be covered in the App Engine sessions. App Engine does not allow you to do threads, does not allow you to do sockets. That's not because they're coded in C, it's because of its very specific execution model. Moreover, App Engine will add some specific APIs such as data store, users, URL fetch, mail, and will support any pure Python module you use. You just put as part of your App Engine application any .py that doesn't use anything except other .pys, and you'll be fine. It will be supported. But back to the standard library. The standard library is so much larger than the language that the time it takes for an expert programmer to master Python, the language, is maybe a couple days. Unfortunately, when he's done that, he's still got a lot of work to do because he probably wants to know the built-ins and the special methods and the metaprogramming, introspection, and so on. And that takes another, say, 3 days. Good. But now he needs to get started with the standard library. Out of the 200 modules, there's maybe 20 or 30 which are absolute must. And those will take another 10 days or a bit more. And when those are done, to really claim they've mastered Python as opposed to the Python language, they probably really want to have a pretty good idea what's everywhere in the standard library that's longer than all of the above. And when they're done with all this, well, there's third-party offerings. I don't know how familiar you are with Monty Python, in honor of which Python, the language, is named. This is a scene from their cheese shop sketch, which I strongly recommend. cheeseshop.python.org is a little bit less clean but better supplies than this cheese shop. It's got 4,000 packages and counting. That I've given up on printing the exact name because whatever I looked up yesterday would probably already be false today. There's more than one package being added every day. It's always fun to roll your own. I mean, if we're programmers, it is because we like to program. So, hey, I need this functionality. I'll roll my own. Unfortunately, that's not a very professional attitude. You probably want to see who else already spent person years of effort into doing this, and this is likely to be on the cheese shop. How long does it take to learn all 4,000 packages? Well, I have no idea. I suspect that if you put yourself to it, by the time you're finished, there would be 4,000 more. So you'd never be finished. So I have no real suggestion here except ask around. Go to the mailing list or go to the Usenet group and just ask, I need to do this and that. Is there some good module you could recommend? You'll probably get 7 recommendations. That's still a lot of work for you to pick the best one, but better than nothing. Remember, online resources, don't forget those. They're all great. You really need that to do really good work in Python. And here we are. We're ready for question and answers. We've got about 8 minutes, so I can field quite a few. If you can please walk to the mic in the corridor and speak your question in the mic.
One question. Google is hosting Dojo and jQuery, the JavaScript libraries.
I'm sorry?
Google is right now hosting for JavaScript development a lot of libraries.
I can barely...
Is this better?
Yes, please.
Okay. Now, Google is hosting some JavaScript libraries that you can load directly from Google, like jQuery and Dojo and so forth. I wonder if there's plans for hosting the stack of third-party modules from Python that you can pull directly.
The reason it makes sense, I'm not a JavaScript expert, but I believe that the JavaScript libraries you require, you mentioned would typically be mentioned in another JavaScript file or a web page and having a URL at which they're certain to be issued. Python doesn't work like that. Python doesn't load code transparently from across the web. You put your code right there. So there's a lot of hosting of open source code that we do at CodeGoogle.com, but that's something you download and integrate with your programs. It doesn't live at any specific URL because that basically would serve no useful purposes.
Yeah, I know. I just thought it would be a cool idea. Sorry.
I see a lot of similarities between Python and Ruby, and I'm wondering what you think are the major distinctions between the two languages.
You could look for my name and the words Ruby and Python, and you'll find about half a dozen places where I've written pretty long essays. But to summarize, if I was doing a spanning tree on the DAG of distances of programming languages, I think the first two to Qualis as being the closest would be Ruby and Python. From the point of view of just about anybody experienced in just about any other languages, they're closer than any two other languages could possibly be. My favorite analogy, being Italian, is that they're like spaghettini and capelli d'angelo. Yes, I could explain the difference. going to be hard if you're not Italian, but I could. Like whether the microscopical are rounded or squared. But in practice, if you're eating them, I challenge you to tell the difference, unless you're Italian, in which case you can, but it's like in the genes.
So I guess my question...
So they're so similar. You can dwell on the differences, but why? In terms of practical consideration, Python is much more mature, so the implementation are of much higher quality because they've been around so much longer. And Ruby is very fashionable, so do you want something solid and working, or do you want something that's like in the news and top of fashion? Your pick. I'm an engineer. I want solid working stuff. Somebody who'd rather be cool can make a different choice.
Are Rails and Django also sort of analogs?
Yes,
in that
except
way?
in this case, Rails has been around longer. So in this case, Rails is more mature than Django. Django's getting there, but it's not quite as rich as Rails is.
Okay, thank you.
Mm-hmm.
How much of this would we have to unlearn when Python 3 comes out?
Oh, so I did specifically mention that you can finally unlearn the distinction between plain strings and Unicode strings. Just about everything else I mentioned is still true in Python 3. The Python 3 removes a lot of stuff that has to be kept around for backwards compatibility, because as long as we're talking about Python 2 dot something, well, it has to keep compatibility. That's a constraint we gave ourselves. Python 3 can break compatibility and therefore can eliminate redundant way to do things that you don't really need anymore. You do have, I did mention that next gains double underscores before and after. That's about it. Yeah.
Well, I've heard that very simple programs like the Hello World program.
Oh yeah,
break.
print becomes a function instead of a statement, right? So you need parentheses there.
Okay.
Yeah.
All right.
Pretty simple.
So you mentioned that monkey patching is considered bad, but
by some, and is considered wonderful by others, and
or in the Python community, I guess you in particular have an issue with monkey patching, but not directly assigning to a module to add additional functionality. Is there a fundamental difference there that you see, or
fundamental difference between what and what?
Between monkey patching and directly assigning to a module, or are they? From my point of view, they're both
modifying a module from outside is monkey patching. That's my definition of monkey patching.
Or, I guess in particular, is there a reason that one is a useful feature of the language and one is something to avoid?
It's useful to be able to fix bugs without editing the buggy code, but it's not something that you should need to do in the long run in production. I'd much rather fix the code, edit the source code, and fix it.
Okay, thank you.
Are there any plans to formally support the notion of interfaces? I know frameworks like Zope.
So Python 3 has a standard library module called abstract-based classes, ABC, which is more powerful than interfaces in some way, although some people think it's less powerful in others. That's basically what we'll have as part of the standard library. Otherwise, you can get third-party packages which support interfaces strictly. There is some stuff that adds absolutely no functionality, but makes you look good.
Is this somehow at odds with the idea that you want to trust programmers?
No, actually, there's nothing against trusting programmers. letting people use abstract base classes. The point is eliminate some redundancy. An interface per se is a structure, well, a way to structure your stuff. It doesn't really eliminate much redundancy. So I'd normally rather, I mean, if you look at some of the ABCs in Python 3.0, they don't actually use the ability to add functionality. They work as if they were interfaces. So, and you can use it so basically, instead of just having to handwave when you're asking me, is something a container? I can tell you, well, it is a container if and only if it matches the container abstract base class. That kind of thing.
Thanks.
Okay. Sorry. Right. So we're done. Thank you very much.